All right, so in this first of two videos on monsoons, we're going to discuss what a monsoon is and what the basic structure of a monsoon is. So let's dive in. So first off, monsoons at a very basic level are characterized by the seasonal reversal of the easterly trade winds. So we've discussed before in this semester how the tropics are characterized by easterly trade winds. Here we're dealing with a reversal of those trade winds so that they become westerly in one hemisphere on a seasonal basis. So in particular, as we'll show, during the local summer months. So the monsoon is driven by seasonal differences in surface sensible warming between the summer and winter hemispheres, with the warming of the summer hemisphere particularly being of land masses due to the different specific heat capacities of land versus water. It takes less energy to warm land by a certain amount than it does to warm water by an equivalent amount. And so here at left, we have a depiction of the Asian or Indian monsoon, a northern hemisphere monsoon that's present during our summer months. The red shading here indicates that the northern hemisphere is comparatively warm compared to the southern hemisphere. And in particular, as we'll discuss for this monsoon, it is the sensible warming of the Tibetan Plateau, the Indian subcontinent and its land masses, relative to the relative cold of the South Indian Ocean that drives the monsoon. So that establishes a meridional temperature gradient, north-south temperature gradient, and it's that difference in warming, diabatic once again, that drives the monsoon circulation. Salient features of the Asian or Indian monsoon, or any monsoon for that matter, include cross-equatorial flow. In this case, at low levels, it is from the cold hemisphere and then spirals and becomes westerly here in the equatorial regions. Note the emphasis of the reversal of the easterly trades here, before spiraling inwards to this area of low pressure associated with the monsoon low. So we have flow from the cold to the warm hemisphere at low levels, whereas at upper levels we have flow from the warm hemisphere spiraling back toward the cold hemisphere. We have our monsoon low here over the Tibetan Plateau in this particular case, and we have the monsoon high in the cold hemisphere at low levels, and these circulation features flip in the upper troposphere. So this variation in where there is convergent low-level motion and by extension ascent with upper-level divergent motion on the seasonal scale is manifest in the Hadley cell's seasonal variability. So as you move from winter to spring and then to summer, the location of the sun's most intense solar heating changes from the summer hemisphere, say the southern hemisphere during our winter, to the new summer hemisphere, our northern hemisphere summertime, such that the Hadley cell also moves poleward with that. That poleward motion of the Hadley cell with the sun is manifest through the monsoon circulation. The monsoon circulation is associated with anomalously wet conditions during the local summer months and anomalously dry conditions during the local winter months. That gives the AM climate classification, the monsoon classification, its name. This is a wet/dry circulation where you have a predominant wet season and a predominant dry season. So let's take a look at the basic structure of a monsoon. So just like we did for the Walker circulation, just like we did for the Hadley cell, we're going to apply some form of diabatic warming to the shallow water equations, or simplified equation set, to be able to obtain the structure of the monsoon circulation. This monsoon circulation, because it is associated with heating that is offset from the equator, as opposed to the Walker circulation, and to a lesser extent the Hadley cell that we previously described, where that warming was centered on the equator, it's going to have a different structure than we saw for the Walker and Hadley circulations. And in fact, it's going to have different equatorial waves comprising that solution than we saw for the Walker and the Hadley circulations. So this structure includes an n=0 mixed Rossby gravity wave, where we had our rotation center here on the equator, and in this case this was the half wavelength that was associated with clockwise rotation, and so thus a high pressure anomaly in the northern hemisphere, where that clockwise rotation is associated with higher pressure, and a low pressure anomaly in the southern hemisphere, where that clockwise rotation is associated with lower than normal pressure. And the other half wavelength of this would be low over high with a broad cyclonic or counterclockwise rotation, cyclonic northern hemisphere, anticyclonic southern hemisphere. Now, in addition to this, we introduce a new type of equatorial wave. This is an equatorial Rossby wave, but instead of being our n equals 1 equatorial Rossby wave, it's now our n equals 2 equatorial Rossby wave. This emerges from the same shallow water equations where we had an n component, which we defined as a generic wave number, and it entered in through a term 2n plus 1. For the n equals 1 equatorial Rossby waves that we considered before, we simply let n equal 1 in the dispersion relation and the structure for those equatorial waves, and that's what we got out. Now we allow it to be equal to 2, and we get a similar but distinct structure. So here, this n equals 2 equatorial Rossby wave is associated with a cyclonic anomaly in the northern hemisphere and an anticyclonic anomaly in the southern hemisphere. Note how the sense of rotation is the same between the two hemispheres. It is counterclockwise in both hemispheres for this half wavelength. So unlike the n equals 1 equatorial Rossby wave, where you had the pressure anomalies be the same between the two hemispheres, here you have the sense of rotation being the same between the two hemispheres. But it has the opposite pressure pattern similar to the mixed Rossby gravity wave, keeping in mind that the other half wavelength of this mixed Rossby gravity wave would be low over high, just like we see here for the n equals 2 equatorial Rossby wave. But unlike the mixed Rossby gravity wave, rotation is within each hemisphere. It is not across the equator. There's very little cross-equatorial flow associated with this n equals 2 equatorial Rossby wave. It does have preferred patterns of low-level convergence and low-level divergence. Similarly here, it is trailing behind the area of low pressure, where you have speed convergence, faster westerly winds slowing down before turning northward. And then here to the east of the area of high pressure, we have weak southerly winds accelerating westward, and this is our location of maximized speed divergence. And so thunderstorm formation is favored on the east side of an area of low pressure and on the west side of an area of high pressure. We could extend this over to here and show this fast westward flow slowing down before turning southward. This is another area of maximized speed convergence, and we'd have the other half wavelength be an area of low pressure to the west. So it's the combination of these two features, and in particular, the opposite sign of this, where you'd have the low in the northern hemisphere and the high in the southern hemisphere for the mixed Rossby gravity wave, that gives the monsoon its characteristic structure. So what does this look like? Here we have output for the velocities, the horizontal velocity in the vectors and the vertical velocity in the contours. And down here we have the horizontal velocity and the pressure perturbations. So we see very clearly that we have the superposition of that low over high mixed Rossby gravity wave and the low over high n equals 2 equatorial Rossby wave. We have counterclockwise rotation given by the vectors or the arrows here in both hemispheres, and this corresponds to low pressure in the northern hemisphere and high pressure in the southern hemisphere. We can use the generic terminology warmer hemisphere for the low pressure and colder hemisphere for the high pressure, because if we have put the warming, rather than here in the northern hemisphere off of the equator, if we put it in the southern hemisphere off of the equator, this would just be mirrored across the equator. So we have counterclockwise rotation with a low pressure in the northern hemisphere and high pressure in the southern hemisphere. We have weak cross-equatorial flow. Note this east-southeasterly flow toward the equator in the southern hemisphere and west-southwesterly flow away from the equator in the northern hemisphere. Where we have our warming applied in this red shaded region, we have our strongest ascent, again to the southeast of the low pressure maximum, as we indicated through the n equals 2 equatorial Rossby wave discussion on the previous slide. We also have this solution being strongest near the equator. Note the horizontal vectors are longest here near the equator and near to the warming source, and they decay eastward and westward, as well as north and south from the equator and from the heating source or warming source, respectively. So if we take a look at the zonally integrated form of this solution, where we integrated along the east-west axis along lines of constant latitude, we get depictions of the zonal velocity and how that varies on the north-south direction, the stream function, which allows us to characterize the north to south flow in the lower and upper troposphere, and the vertical motion between the two hemispheres, as well as the pressure perturbation and how that varies on the north to south axis. So starting with our zonal velocity here, in the lower troposphere, we have westerly flow in the warmer hemisphere, this being the northern hemisphere in this example, and easterly flow in the colder hemisphere, this being the southern hemisphere in this example. And in the upper troposphere, it's the opposite. You have easterly flow atop the low-level westerlies in the northern hemisphere, the warmer hemisphere in this case, and we have westerly flow atop the low-level easterlies in the southern hemisphere, the colder hemisphere in this case. We have cross-equatorial flow, so going from the southern to the northern hemisphere at low levels, and from the northern hemisphere to the southern hemisphere at upper levels. We also have tropospheric deep ascent. Our warming was applied in the northern hemisphere, and we have rising motion through this latitudinal range. So this too is a thermally direct circulation, just like the Hadley cell, just like the Walker circulation, sorry. We also have tropospheric deep descent here on the backside of the circulation in the colder southern hemisphere. We have low sea level pressure here in the northern hemisphere, maximized just northward of the warming source. We have high pressure in the southern hemisphere, in the colder hemisphere, maximized an equal distance away from the equator as the warming source was the low pressure was maximized in the northern hemisphere. So this circulation here with ascent in the northern hemisphere and descent in the southern hemisphere closely resembles the Hadley circulation that we would expect to see during northern hemisphere summer. If we were to put the warming in the southern hemisphere, this would be flipped and it would closely resemble the Hadley circulation we see during the southern hemisphere summer. And in fact, this solution for the Hadley cell more closely represents the overall Hadley cell than does the symmetric heating case. But there's one caveat here because the heating is not always asymmetric across the equator. There's often a component that is centered on the equator and offset from the equator. So what does that look like? So fortunately, Gill 1980 also took a look at what that looks like. And here we have the same schematic structure as we did a couple of slides previous, with our velocities here on the top panel and our horizontal velocity, as well as the pressure perturbations here on the bottom panel. So the combination of symmetric and asymmetric warming is the combination of 4 equatorial waves. Recall that our symmetric warming solution had the combination of a Kelvin wave and an n=1 equatorial Rossby wave, specifically the cyclonic half wavelength of that. And then for the asymmetric warming, we had low over high in the northern over the southern hemisphere half wavelengths for the mixed Rossby gravity wave and the n=2 equatorial Rossby wave. And so the combination of all 4 of those waves gives us the solution that we see here. Now this is characterized by constructively interfering waves in the warmer hemisphere. That means that all of those wave structures are associated with anomalously low pressure and counterclockwise rotation. Our cyclonic half wavelength of the n=1 equatorial Rossby wave was cyclonic in terms of its rotation, and so too was the northern component of the mixed Rossby gravity and the n=2 equatorial Rossby waves. So those 3 all add together and give us this strongly cyclonically rotating feature in the northern hemisphere, offset somewhat north of the equator, with strong low pressure in association with that feature. Conversely, in the southern hemisphere, we have destructively interfering waves, where it is relatively cool. So in the equatorial Rossby wave, the n=1 equatorial Rossby wave solution for the symmetric warming, we had a cyclone in the southern hemisphere, whereas for the n=2 equatorial Rossby wave and the mixed Rossby gravity wave, we had an anticyclone there. So we are offsetting the intensity of the anticyclone through that cyclonic rotation with the n=1 equatorial Rossby wave. And so consequently, we have a relatively weak area of high pressure with relatively weak counterclockwise rotation in the southern hemisphere. Note that we have strong cross-equatorial flow here across the equator, curving from easterlies in the colder hemisphere to westerlies in the warmer hemisphere. We have strong ascent through the combined warming source, which is located from the equator, extending northward from there. And we have the Kelvin wave solution extending far to the east and somewhat to the west from this as well. If we meridionally integrate this, so if we look at this at constant longitudes, we get something that very closely resembles the Walker circulation. If we integrate this zonally along lines of constant latitude, we get something that closely resembles the Hadley circulation. The combination of these four equatorial waves in response to the combination of symmetric and asymmetric warming across the equator provides a circulation in the north-south direction, our meridional overturning circulation, that has an intensity that's very close to what we actually observe for the Hadley cell. And it's about 65% of that which we see with the zonal overturning Walker circulation, which also closely resembles observations. So this is yet another example of diabatic warming driving tropical circulations. In this case, differences in diabatic warming between hemispheres offset from the equator. In our next video, we're going to take a look at a number of the monsoons that we see across the world and briefly discuss the variability that we see in association with them.